Tortuga Field is an undeveloped oil field located in the Gulf of Mexico. The field sits beneath 1,935 feet of water and at a total vertical depth of 18,250 feet. The host platform to be used during production sits at sea level and the deck is 92 feet above it. The oil field development consists of two producing wells in which wet tree completions, along with a shared dual line, will help transport hydrocarbons the 12-mile horizontal distance to the platform. The objective of our project was to perform a high-level analysis to maximize the field's production. Though time to produce the reservoir was a major factor, time to reach EUR was not our only consideration. We decided to also emphasize costs associated with completions and producing the well in a manner that would maintain the integrity of our equipment as well as the formation while minimizing any losses or downtime associated with equipment failures. To achieve our objective, we have divided our approach into three phases. The first phase was to develop an accurate model of the reservoir and associated production equipment. We used known data about the reservoir and available equipment along with knowledge from this course and the spreadsheets provided by Dr. Waltrich to establish an accurate base case. The second phase involved examining the effect of changing individual parameters on the system as a whole. The parameters included choke opening, wellbore and tubing diameter, different completion types, and changes in separator pressure. The final phase involved combining the effects to provide recommendations for optimal production of the well. Here we have listed given equipment and PVT data. Please note the items highlighted in orange. These items are the individual parameters that we will be adjusting during our trial runs in order to provide recommendations for optimization at the end of our presentation. Here we have listed the given reservoir data. This data is typical of Tortuga Field and will remain constant throughout our analysis. Using the given PVT and reservoir data, in addition to some fluid correlations from the McLean Petroleum Fluid Properties textbook, we were able to establish that the time until pseudo-steady state flow occurred was 9.2 days. At this time, the average reservoir pressure was 12,982 psia. We calculated these using the transient and pseudo-steady state flow equations in addition to the time until pseudo-steady state flow equation. We have broken our system into four components. We've used a modified Vogel to model the reservoir, Haggard and Brown to model the wellbore, the Gilbert correlation to model the choke, and Beggs and Brill to model the flow line.
On Excel, we created a chart to track our runs from the given spreadsheets. The runs were conducted every 3 months until our EUR of 5 million stock tank barrels of oil were produced. On the chart, the 9 highlighted columns show the parameters we collected from each run. It includes the time in 3-month periods, wellbore pressure, oil flow rate of a single well, the wellhead pressure, and the pressure downstream of our choke. The highlighted columns provide the parameters we calculated using the data from our runs. These columns include average pressure, total oil flow rate of the 2 producing wells, whether our condition of wellhead pressure being greater than pressure downstream of our choke was met, and the change in the average reservoir pressure. As engineers, we had to make a few assumptions before we began the simulations. Both wells were assumed to transition into pseudo-steady flow after the initial transient flow. We based our pressure profile, IPR TPRs, and production curves on the result of pseudo-steady flow. Since pseudo-steady began at 9.2 days, we assumed the transient flow was negligible to our 3-month intervals, and we used this as the basis for the production curves. We assumed critical flow boundary was initially established as a limitation for testing. This ensures changes downstream of the choke at the platform will not affect the production. Due to a short length of 200 feet, flow through jumper lines was neglected. It also had a minimal impact in the pressure drop and flow rate. Beggs and Brill equation was used to model the entire dual line to the platform. We found the largest inclination along the seafloor to be approximately 40 degrees. This is the base case IPR with the TPR for year 0. Year 0 yielded the highest average pressure at 12,982 psi. The IPR curve is linear while the fluid is in single phase and begins to curve when wellbore pressure goes below bubble point where fluid then becomes introduced to gas, resulting in a two-phase flow. At year 0, max flow rate was just under 100,000 stock tank barrels per day, while years 1 and 2 were 88,600 and 80,000 barrels per day respectively. Due to the TPR at year 0 being so high, the flow is constrained, therefore the max flow potential will not be achieved. Drop and flow potentials are respective to the average pressure drop, where the change in average pressure is proportional to flow rate. On the cumulative production and production curve, the blue line represents flow rate, while the orange line represents cumulative production. Max capacity of the Tortuga reservoir is 5 million stock tank barrels. The estimated ultimate recovery is reached at just under 3 years. Flow rate decreases as time increases. The initial combined flow rate of the two producing wells is 5,714 barrels per day. And as mentioned before, the EUR was achieved at just more than 34 months. On the base case pressure profile, the initial average pressure was at 12,982 psi, and as flow migrated towards the choke, the pressure gradient dropped linearly. Once at the choke, there was a significant pressure drop, and this satisfies our sonic flow condition. Once at the choke, the flow goes up the riser to the platform, and a constant pressure gradient as well, where it is then flowed into a separator on the platform.
In this portion of our analysis, incremental choke openings of 12/64ths, 20/64ths, and 22/64ths of an inch were examined, in addition to the base case of 16/64ths of an inch. Using the formula for volumetric flow rate, where flow rate equals velocity times area, our group assumed that as the choke opening was increased, the resulting flow rate from the well would increase as well. This in turn would result in a shorter period to reach estimated ultimate recovery. Our first trial run was at a decreased choke opening of 12/64ths of an inch. The resulting pseudo-steady-state IPRs for the run at initial pseudo-steady-state conditions, 1 year and 2 years, are shown below. As time passes, our IPRs show that the average reservoir pressure decreases over time, along with the production associated with each time. Production curves were also produced for the choke opening of 12/64ths of an inch. The graph below shows that estimated ultimate recovery was reached in just under 5 years. The production flow rate curves show an initial production of approximately 3,400 stock tank barrels per day that reduces to just over 2,000 stock tank barrels per day over the life of the well. This choke opening, when compared with the base case, increased the time until estimated ultimate recovery by 73% and reduced both the initial and final flow rates by 41%. The IPR curves for increased choke opening of 20/64ths of an inch are shown below. Again, the IPR shows that the average reservoir pressure and the resulting production at each time period decrease over the life of the reservoir. Since the pressure drop in the reservoir is a function of flow rate, the set of IPRs exhibit larger decreases over time than the previous runs. This is due to the larger flow rates observed for this choke opening. The graph below shows that the estimated ultimate recovery was reached in approximately 1.8 years. The production flow rate curve shows an initial production of approximately 6,500 stock tank barrels per day that reduces to just over 3,000 stock tank barrels per day over the life of the well. From a comparison with our base case, we find that estimated ultimate recovery is reduced by 36%, initial production rate is increased by 14%, and the final production rate is increased by 34%. In addition to the runs already discussed, simulations were carried out at 22/64ths and 24/64ths of an inch as well. These runs were not included either because initial production exceeded the 10,000 stock tank barrel per day capacity of our separator, or our critical flow condition, PWH is less than 2 times P2, was not met. This condition is important to us because it allows for the system to be decoupled and ensures the validity of the equations we used when modeling the system. From these graphs, we can observe that as choke openings were increased incrementally, flow rates from the well increased, and time to reach estimated ultimate recovery decreased.
After evaluating the chokes, we look to the effect of the completion type. There are 3 typical completion types: open hole, cased and perforated, and gravel packed. All are seen here. We use different correlations from the Economites book to evaluate the skin and interpret the effect of the completions on the IPR and production histories. The damage zone from drilling is said to be 11 inches from the center line and to have reduced permeability from 600 to 100 millidarcies. The base case open hole yielded a skin of 3.03 when evaluated with the Hawkins formula, while the perforated skin was 2.24 for a perforation length extending past the damage zone, and gravel pack yielded a skin of 4.13 for a 4-inch thick gravel pack. Now looking at the IPRs, we can see that there is little variation between the two alternative completion mechanisms. Noting that these IPRs have been overlain with the base case IPRs, we can see how little the completion type changes the flow potential of the well. Looking at the production histories, there is also very little deviation from the base case in terms of time to produce the EUR. Seeing that the completion mechanism was a non-essential factor, I decided to further evaluate the gravel pack with a partial completion. Graphing partial completion skin versus completion length shows an interesting trend. For completions between 30 and 80 feet of the 80-foot thick reservoir, the trend in the skin is linear. However, completing less than 30 feet seriously impacts the production potential of the well. Noting the small size of the field and the small time it will take to produce, it seems prudent to minimize the upfront costs of the well. Partial completion reduces the initial costs, and the lower flow rates associated with it can be compensated with a larger choke opening. Hence, we agreed on a gravel pack to reduce sand production and a partial completion to reduce cost.
The next variable we changed on the Tortuga well was the wellbore inner diameter. We then noted changes in production. As observed from the formula here for pseudo-steady single-phase flow in a reservoir, an increase in wellbore radius, the term R sub W, is going to increase the flow rate. Similarly, a decrease in wellbore radius is going to decrease your flow rate. This is, of course, when all other properties are held constant. The base case wellbore radius was 6 inches. We reduced the wellbore radius to 5 inches to observe production over 3-month periods until we produced all of the allotted reserves of 5 million barrels. This well produced all of the reserves nearly 16 hours slower than the base case, and the initial flow rate was 4 barrels per day, lower than the base case. Marginally different, but a clear decrease in production. Shown here are the IPRs for the reduced case of the 5-inch wellbore inner diameter at initial pseudo-steady flow, 1 year, and 2 years of production. A clear decrease in performance from the base case, which had a max flow rate of 99,445 barrels per day, is seen. This is a difference of 1,555 barrels per day, and the initial average pressure was also higher by 1.2 psi. The next trial was an increase in wellbore radius from 6 inches to 7 inches. This well depleted the reserves of the reservoir in 1,023 days, a full 24.5 hours faster than the base case. The initial flow rate was also 10 barrels per day faster than the base case. Also not an incredibly significant difference, but a clear improvement from the base case. If this reservoir had a larger reserve, this change would be more significant over time. Here's the inflow performance relationship, or IPR curves for the increased wellbore radius. An improvement was also noted in an increase of maximum flow rate to 100,810 barrels per day from 99,445 barrels per day, an improvement of nearly 1,400 barrels. Also not an incredible improvement. The IPR curves were not plotted on the same plots for the different cases because the lines were practically overlapping. The next variable we altered was the tubing inner diameter to note the changes in production. We reduced the diameter and the reserves were depleted almost 10 days longer than the base case diameter of 4.5 inches. This was using a tubing inner diameter of 3.5 inches. The initial flow rate was down from 5,714 barrels per day to 5,652 barrels per day, a decrease of 62 barrels. Here's the tubing performance relationship for the reduced case in yellow compared to the base case in green, plotted on the IPRs for the base case. Due to the not very dramatic change, it's hard to note by sight the difference in the plots, but the base case has a point of natural flow at 2,855 barrels per day, and the reduced case has a point of natural flow of 2,799 barrels per day, so a decrease in tubing performance was noted. Next, we increased the tubing diameter to 5.5 inches from 4.5 inches. This showed another improvement in production, depleting the well reserves 3 days faster than the base case. The initial flow rate increased from 5,714 barrels per day to 5738 barrels per day, a 24 barrel increase. Here are the TPRs for the base case plotted in green and the increased tubing in blue. The point of natural flow occurred at 12,676 psi compared to the base case at 12,672 psi, meaning the base case will flow at a lower pressure than the 5.5 inch. Also to be noted was a decrease of 35 barrel per day from the base case to the increased case. Here are the TPRs for all three cases plotted on the IPRs for the base case. In summary, the 5.5 inch tubing did produce 3 days faster than the base case, but a higher pressure is required for natural flow. The reduced case produced nearly 10 days longer than the base case. These differences were notable, but not incredibly dramatic. To determine the most optimum case, the prices of each tubing must be taken into account. Due to the short-term nature of the well, using the cheapest tubing, in this case the 3.5 inch, may be the best choice. Small changes in tubing size can account for much larger changes in well costs. A basic 2 7/8 inch production tubing from Borland and Leverage costs $3.55 per foot, whereas a 3.5 inch basic tubing costs $6.39 per foot, meaning this well would cost close to $52,000 more by increasing the tubing by just over half an inch. As you could imagine, 4.5 and 5.5 inch tubing would be even more expensive. Due to the short-term nature of this well, the 3.5 inch tubing would be most cost-effective. Runs were not conducted for the case of an increase or decrease in separator pressure. All runs were conducted within the critical flow boundary where pressures at the wellhead were less than 2 times the pressure at the downstream end of the choke, P2. Therefore, changing separator pressure would not change production. If the critical boundary were exceeded and runs were conducted at these pressures, increasing separator pressure could decrease flow rate from the reservoir, and decreasing separator pressure could increase flow rate from the reservoir.
The analyses show that it is possible to produce the entire contents of the reservoir in as little as 1 year. However, this Cadillac approach is likely to reduce the EUR as well as to damage the production equipment from unnecessary sand production. Thus, we favor a more conservative approach that does not significantly alter production times. We propose a 40-foot gravel pack partial completion flowing through a 3.5 inch tubing through 1664-inch choke. To arrive at this optimized case, I first evaluated a well with these parameters, but with a 1264-inch choke. As seen on the Optimization 1 chart, this choke opening nearly doubled the time to produce the well. So on the next run, I opened the choke to 16/64. This brought production time down to 39 months. This seemed to be a reasonable time and did not represent a fully open choke. Overall, Optimization 2 is preferable to Optimization 1. Looking to the IPRs and TPRs, we see the same shape and a little deviation from the base case. So we decided on this as our optimized case. In the end, using a small tubing and completing only half the interval will reduce the upfront cost of the well. Analysis shows that smaller tubing does not significantly affect the flow rate of the well at any given point in time. Completing just 40 feet of the reservoir only increases skin by a factor of 8 and does not yield an appreciable difference in flow rate. It is beneficial because it reduces costs and could mitigate sand production via a smaller flow area. The gravel pack completion will further reduce sand production. To maintain a high flow rate with these conditions, we propose opening the choke to 16/64. Combining these parameters, we aim to produce the entire contents of the reservoir within 40 months, which is comparable to the base case. Overall, our approach yields the same gross revenue while minimizing costs and damage to the equipment.